Hello, welcome back to Math with Patrick. Today's June 7th, and we're solving problem number 158 from the Daily Epsilon calendar. And we need to find the smallest n such that a regular n-gon cannot be constructed with a straight edge and a compass. All right, what's a regular n-gon? Is a good question to ask before we get into it. An n-gon is just some kind of polygon with n amount of sides. So like a 3-gon is just like a triangle. A 4-gon is just a quadrilateral. It could be a weird one, kind of like this. A 5-gon is a pentagon, so on and so forth. But if I want them to be regular, I just need all the sides and angles to be the same. So a regular 3-gon is going to be an equilateral triangle. All angles are 60 degrees. And then a regular 4-gon is just a square because all the sides are the same and then all the angles are the same as well. So like a regular 5-gon is basically what you expect a pentagon to look like, as with a regular 6-gon is just what you expect a hexagon to look like. Now let's talk about this whole straight edge and a compass thing. Whenever we're doing constructions, there are maybe rules that you follow or shouldn't follow. And when we're talking about constructing stuff with a straight edge, that just means like a ruler. But specifically, it's not one that's marked. As in, I don't know any distances along the straight edge. I just know that it's a straight line. The compass part, this is not, north, south, east, west compass. This is one that kind of looks like this with like a little divot here and then like a pencil tip here or a pen. And the compass lets us draw circles. It lets us move around lengths on the paper. Because if I have a length here and I flip around my compass to the other side, I can kind of copy the same length on the other side. And so there are certain things you can do with a straight edge and a compass, like create some polygons. And there's a few things you can't do. So how about let's actually go to like a different clip. I constructed the 3-gon, 4, 5, and 6-gons of the regular varieties. And you can kind of see how I use a straight edge and a compass to create those. So here's my straight edge, and there's my pencil, and there's the compass I'm going to use. And so to start out, we are going to start constructing the 3-gon, or just a triangle. So you can use the compass here to kind of rotate lengths around the paper. And so since those are two circular arcs, these lengths that I'm drawing right now are going to be the exact same length as the base. And so since I have 3 lengths, all the same size, it's going to be a regular 3-gon or an equilateral triangle. So that one's pretty straightforward. We can just kind of rotate lengths to kind of copy them to different places on the paper. Now the regular 4-gon, or the square, is a little bit different. Right now I'm using a technique where I'm trying to find a perpendicular line to another. And so it starts out by like finding these arcs on 2 different sides of a point. And then just kind of based on symmetry, we can create 90-degree angles with this method. So here is one of the 4 90-degree angles, and now I'm constructing another one. I'm making 2 marks on either side of this point. And then from those 2 new marks, I'm now making these larger arcs. And where these larger arcs meet over on the top there is going to be exactly 90 degrees to that original point around which I made a circle. So now I have 2 right angles. Both of those lines are now parallel to each other. And so all I'm doing is kind of that strategy from the triangle earlier, where I'm rotating around equal lengths in a circle. And then so now I have all 4 points of my square. So one more line, and that does it. I have now constructed a square with a compass and a straight edge. Now the pentagon is probably the hardest of these. I'm going to start out by drawing this circle, and I'm kind of struggling, honestly, to draw this circle with this compass, but I make do. I'll mark the center there as well. And the process is kind of convoluted. Here, all I'm really doing is that kind of 90-degree strategy right now. I don't really need to use it, honestly, because I could draw any diameter across the circle to start out. but I just wanted mine to be like as vertical as possible. So that could have been any diameter. It didn't really matter. But this is where it does matter. I do need a 90-degree angle away from this new diameter to draw a radius. And so here I'm using the same strategy from the square to find a nice perpendicular line to another. And so here is that perfectly, well, ideally, perfectly perpendicular radius to my diameter. I'm once again using the strategy of a 90-degree angle to find the midpoint of my radius, because I'm going to, once I find that midpoint, mark it as the center of yet another circle. So this whole process of creating the pentagon is kind of convoluted, and later on the whiteboard, I do want to show why this actually does create a pentagon. Here I'm struggling even more with this circle. The smaller circle isn't quite hitting the edge of the larger circle, and it should, right? Because I constructed the midpoint of that radius, and so ideally this circle should be going, or the diameter of this smaller circle should be equal to the radius of the bigger circle. But oh well, it doesn't line up perfectly. I mean, I think it turns out to be fine. And this length right here is going to be super, super important for my proof later on the whiteboard. Ultimately, once I rotate this length towards the larger circle and I find where it intersects the larger circle, that length kind of forces the final construction here to be a pentagon. So there's 1, there's 2, 3. I'm making all of the different sides or edges of my pentagon, 4 and 5, and it lines up roughly back at the start. And so all 5 of those points are going to make that regular pentagon. So here I am just connecting them all to finally construct the pentagon. And fortunately, the hexagon is a little bit easier. It uses some of those ideas from the triangle. And so once I'm done drawing this pentagon, you'll see that constructing the hexagon will be much quicker. All right, starting out, drawing another circle. And then it kind of looks like I'm gonna start doing those like halfway point arcs, because I did one of these in the pentagon. You can kind of see how I have one of those arcs in the pentagon, kind of on the right side of the pentagon there. But instead of actually finding those halfway points, the midpoint of those radii, it's just the 6 points on the edge of the circle that create the hexagon. And maybe you can believe or convince yourself that this hexagon indeed is regular, because it's essentially just made up of 6 equilateral triangles. All of those degrees and the triangles are going to be 60 degrees each. So ultimately, I get a regular hexagon. So there we go. Those are constructions for the first 4 n-gons. So first, let's show why this construction even makes a regular pentagon before we hop over to kind of proving why we can't create a heptagon for 7 sides. So here's that diagram. We got a circle. We got a smaller circle on the inside. Let's just say that this radius is 2. I think that one's going to be like the easiest one to work with here. Because if this radius is 2, then half of the 2 will be a 1. So the inner or the smaller radius for the smaller circle is 1. We can use some Pythagorean theorem to show that this is the square root of 5. And then finally, here's that total length that we were working with. This will just be 5 plus, or root 5 plus 1, because here is another of that like small circle radius. So once I rotated that length to this side, here is yet another segment with the length 1 plus root 5. I want to copy it over to the left side just so it's a little bit clearer what I'm doing. So this length right here is 1 plus root 5. And I can create a triangle right here in the circle. And using the central angle theorem, noticing that this right here is 180 degrees, half of that will be the angle here. And so this shows that I have a right triangle with a 90-degree angle in the corner. This 2, that was the radius, can kind of help us see that 4 is the diameter. And so now I have 2 lengths of this right triangle, and we can use some trigonometry to figure out some of the angles here. how about let's figure out this angle up top. I know that sine of this angle is going to be opposite over hypotenuse. So sine inverse of opposite over hypotenuse is going to get us precisely the angle there. If you ask a calculator, this is 54 degrees. And then finally, once we double that value, we would get 108 degrees. And that's precisely the necessary value to create a regular pentagon. So a little bit of trig, a little bit of geometry, we can show that this method gives us a regular pentagon. Finally, a short proof as to why a heptagon wouldn't work is one where you can look at the angles of all of our polygons. With the straight edge and the compass, you can add and subtract angles with each other pretty easily. So like here we can see that, we created like a 108 degree angle. And so you're allowed to or you're able to bisect angles with a straight edge and a compass, kind of in a similar way where I was able to find like 90 degree angles. You can also bisect them with these tools. So like finding a 54 degrees is possible. And then finding half of this would also be possible, which would then be, 27 degrees? Yeah. And so these are all constructible angles with a straight edge and a compass. 90 degrees, you saw that we could create that. So 45 degrees is constructible. And so even decimal angles are constructible too if we keep finding these bisections of angles. So like 22.5 is doable. But one thing that's kind of known that you can't do with a straight edge and a compass is trisect angles. So we could create a 60 degrees, right? We did that in the equilateral triangle, but you can't trisect angles here. So we couldn't really ever create a 20 degrees. Also with these ideas of like bisecting is possible, adding is possible, if you try all these combinations, you're eventually going to get down to a claim where any multiple of 3 degrees is going to be okay. And any halving of any of those angles is also going to be okay. So let's keep that in mind. And let's figure out what the internal angle of a heptagon is going to be. We're going to have 1, 2, 3, 4, 5, 6, 7 sides. Sorry, that doesn't really look that accurate. And if you draw all of these internal triangles, you could figure out that the sum of all of these triangles, angles altogether, will give us the sum of all the angles in a regular heptagon. So multiplying this by 5, we have 900 degrees total. And when you split this amongst the 7 angles, we're going to get kind of a weird angle. It's going to have this kind of nasty decimal attached to it. It's 128.57 degrees. I'm using a calculator right now on my phone. This 0.57 at the end is 4/7. And unfortunately, this fraction we just couldn't create with the constraints of the rules that we have. There's no number out there that could be a multiple of 3, and then maybe you might apply some successive dividings. Like there's nothing that's going to help us divide by 7 within those rules of a straight edge and a compass. So there are some approximations. There are also ways to construct it with a marked straight edge, something that has an actual length that's usable on the straight edge. But there's no way for us to do it within the rule set of straight edge and compass. We won't be able to find a number that's a multiple of 3 that we can successively divide by 2 to reach this. There are also other proofs out there of why a heptagon is non-constructible. There's other ones that kind of involve lengths instead of angles. And so feel free to look those up yourself if you want to kind of confirm that indeed we cannot create a regular 7-gon or a heptagon today. So that's all I got today, but I'll see you tomorrow for the next video. Alrighty.